Hi everyone, it's Mr. Hamilton here. Today we're going to talk about composite functions. We're going to deal with the basic definition of what a composite function is, that's in bold here. Then we're going to describe the function that the order at which you make composite functions matters. These two things are not the same, and we'll understand why. And then we'll do the three examples that are shown there. So a composite function means putting one function inside the other, kind of like nesting dolls. You open up the bigger doll and you can fit the smaller one in, etc. They go one inside the other, inside the other. And so when you package them all together, they're all look like one doll, but they're all inside that one doll. So in terms of composite functions, we could write a composite function h of x equals f of g of x. So what we're doing is we're putting the function g of x inside of f of x. What that means is that we take the y values from g of x and use them as the x values for f of x. So there it is on your screen now. We take the y values from g of x and we use them as the x values for f of x. And so this also means, and this is very important, that the order matters. The order matters. So what we're going to do is we're going to start with that first example and show you why that order matters. So the first example was that f of x, this is example 1, f of x is equal to x squared, and g of x is equal to x plus 2. And so what that means is if I go h of x, if I say that that is f of g of x, then what that means is wherever I see the x in f of x, I'm replacing the x with the g of x, which is x plus 2. So I'm saying it's basically f of x plus 2. So I'm taking that x plus 2 and replacing the x with x plus 2. So this could be written as x plus 2 all squared. So what I've done is that x plus 2 is nested inside the x squared function. And so that is the first function if it's f of g of x. Well, what if it was g of f of x? Well, if it was If we said that, let's call that something else. Let's call it k of x, just to be different there. This is g of f of x. If that's the case, then we're going to nest x squared inside of x plus 2. So this is g of x squared. And so that means everywhere I see the x in g of x, I'm replacing it with x squared. So this will be written as x squared plus 2. So k of x is x squared plus 2, and we can clearly see that's not the same thing as h of x, which was x plus 2 all squared. Those are two different things. In fact, if you expand this out, you end up getting x squared plus 4x plus 4. That's a perfect square. And so these two things are clearly not the same. And so that means that we could say that f of g of x is not equal to g of f of x. That's one example, but you can see that that pattern would follow for anything, provided they're not really the same function. If they were both the same function, then it would work. But anytime you have f and g of x being different functions, and one is not the inverse of one another, that'll be our last example, this is going to apply, that those two things are not the same thing. The order matters. But sometimes you're given a number to sub in. So what would happen if the question instead said determine h of 1? Well, there's two ways you could do that. You could take the function that you've already determined, and you could say h of 1 is equal to, we had x plus 2 squared, so that'd be 1 plus 2 squared, which would be 3 squared, which would be 9. Or you could say that h of 1 is equal to f of g of 1, because the original x value is 1. That's what it means to sub that number in. So what we could do here is we could say that it's f of, well, what was g of 1? Well, this is 1 plus 2. Well, this is f of 3. Well, what was f of x is x squared, so then that would be 3 squared. Well, what was 3 squared? It's 9. So whether you take h of 1 and substitute 1 in for the original x value and work on g of x then f of x, or you work on h of x directly, they both work. So here's our second example, example 2. The example is this: f of x is equal to x squared plus 3x plus 2, And g of x is equal to 1 over x minus 2. So we have this quadratic and we have this rational function. And so if I'm asking you to find h of x equals f of g of x, what you're going to do here is you're going to put the g of x first inside the f of x function. So in other words, it's f of 1 over x minus 2, because that's what g of x is. I'm replacing g of x as 1 over x minus 2. So everywhere we see the x, we're replacing it in the f of x function with 1 over x minus 2. So this is going to look like this. I have an x squared. I'm going to replace that with 1 over x minus 2, all squared. And then plus 3, and I have a 1 over x minus 2, and then plus 2. And that, I could take that further and simplify it further, but that is what h of x would be. If I asked you to find k of x, and that was equal to g of f of x, well, we know that f of x is x squared plus 3x plus 2. So we're replacing the f of x with that function. And so now everywhere we see the x in the g of x function, we're replacing it with x squared plus 3x plus 2. So this is going to become 1 over x squared plus 3x plus 2 minus 2. That was still there. So this is what the x was replaced with, the x squared plus 3x plus 2. And I could simplify that to give me 1 over x squared plus 3x, because the plus 2 and the minus 2 are going to cancel. So what we can see here in the denominator is that x cannot be, in this one, if we factor, I'm going to take it one more step here. This is 1 over x times x plus 3. And so that means that x cannot be 0 and x cannot be negative 3. Up here, in this function, we had that x cannot be positive 2. That was our only restriction there. And so the restrictions actually change depending on how you do it, not only the function. Both the restriction and the function change. The order depends. Now, if I said, let's do determine, again like we did before, h of 1, that means that I'm going to substitute 1 in everywhere there's an x. So you could do that directly. So you could say h of 1 is equal to 1 over 1 minus 2 all squared plus 3 times 1 over 1 minus 2 plus 2. That would give you 1 over negative 1 squared, which is just 1. Negative 1 squared is 1. Plus 3 times 1 over negative 1 plus 2. So negative 1 squared gives me 1. 3 times negative 1 gives me negative 3, and then positive 2. And so that would give me 1 minus 3 is negative 2, plus 2 is 0. Alternatively, you could do it the same way we did it earlier. So let me go back, let me go down a little bit and show you what that would look like. If I said h of 1 is equal to f of g of 1, well, what was g of x? G of x was 1 over x minus 2. So you could go f of 1 over 1 minus 2. And so then we could say f of 1 over 1 minus 2 is negative 1. And then we're substituting negative 1 into f of x. Then we get negative 1 squared plus 3 times negative 1 plus 2. Well, that gives me 1 minus 3 plus 2. And lo and behold, it's the same answer. It's also going to be 0. So you have both of those ways that you could solve it when you were given a number. All right, on to the last example now with the inverse. On to example 3. So example 3 is this. Y equals f inverse of f of x. F inverse of f of x. And so f of x is going to be equal to 2x plus 3. So what does that mean the inverse function is? Remember, an inverse function is this. We let y equals f of x, and then we switch x and y. In effect, it's undoing what the function does. So if I'm adding 3 and multiplying by 2, I'm going to subtract 3 and divide by 2. But I'm going to just take you through this step so you can see how to calculate the inverse every time, regardless of whether it's linear or much more complicated than that. So switching x and y gives me x equals 2y plus 3. And now what I'm going to do is I'm going to do the reverse order of operation to rearrange the equation. So we're going to do SAMDEP. Normally we do bedmiss if we know all the values and we would follow those to get an answer, but to rearrange an equation, we do SAM-DEB, bedmiss in reverse, the opposite order. So what I'm going to do is I'm going to subtract 3 from both sides. That's my subtracting step. There's no adding to do after that, so I get x minus 3 equals 2y. So the subtracting and adding is done. Now I do my multiplication or dividing, and so you can see here that I have to divide by 2. And so y equals x minus 3 over 2 is the inverse function. So I can write this as f inverse of x. It's quite a line. F inverse of x is x minus 3 over 2. All right, so now that we've got the inverse and the original function, let's go ahead and figure out what f inverse of f of x is. So this means f inverse of, well, f of x is 2x plus 3. So if I substitute 2x plus 3 in everywhere I see the x in the original, or in the inverse function, because that's what I'm substituting it into, what I'm going to be left with is, I'm going to be left with 2x plus 3 minus 3 all over 2. And what you can see here, if I get rid of the brackets, you don't need to get rid of the brackets to see how the math works out, but just if that helps you to see that, we get positive 3 and negative 3. That gives me 2x over 2, and that just gives me x. Y equals x. That's significant, because what that means is that whenever a composite function is taken with its inverse, when you take f inverse of f of x, or if you take f of the f inverse of x, you're always going to get y equals x, because the inverse undoes all that the original function did, and vice versa. You're always going to arrive at y equals x. There you go. All right, the last thing I'm going to do in this video is just give you some common examples of composite functions and describe what the inside function is and the outside function is, and then we'll be done. So common examples of inverse functions. So y equals 2x plus 1 all to the power of 7. And so the outside of this would be to the power of 7. And then the inside of this would be 2x plus 1. In other words, this would be the same thing as if f of x was equal to 2x plus 1, and g of x is equal to x to the power of 7, and h of x would be equal to g of f of x. Those two together would give you 2x plus 1 all to the power of 7. Let's look at another one. What about y equals sine to the power of 3x, sine cubed x? Well, that's the same thing as sine x all cubed. We just write it in shorthand as mathematicians, just so we don't have to write the brackets every time. So what's the outside? Well, the outside of this is the cubed, or x cubed, and then the inside of this is the sine of x. So if I have f of x is equal to sine of x, and I have g of x is equal to x cubed, then h of x would be g of f of x. In other words, you would take the sine x, put it in place of the x, and then you would cube it. And so you get x cubed. All right, what about another one? How about this one? Y equals sine of x cubed. Notice the cubed is in a different space here. The outside of this function is actually sine of x. And the inside of this function is actually the x cubed. That is, it's operating on the x cubed. So in this case, your f of x function would be x cubed, and your g of x function would be sine of x. And so if your h of x function was g of f of x, then you would say I'm taking the x cubed function, and then I'm putting it in terms of where I see the x in sine x. And so you get sine x cubed. Last one would be this. Y equals log of 2x cubed minus 4. Outside, well, that's log of x. And the inside, we can see that that is 2x cubed 2x cubed minus 4. So that means that if f of x was 2x cubed minus 4, and g of x was log of x, then h of x would be the same as y here, which would be g of f of x. In other words, I would take the 2x cubed minus 3, put it in here for f of x, and then log of, I'd replace the x with 2x cubed minus 4. There you go. There's some common examples of inverse functions, and if that was helpful, please give it a thumbs up and feel free to subscribe. Thanks.